Okay, this is a wonderful session. I'm learning in every single talk so far. That's a joy. This is something of a perspective um, piece for you, a perspective talk. I'm going to give my personal experience attempting to apply machine learning and related techniques. I say related because I teach statistics. And the phrase machine learning troubles me. We can talk about that over lunch. But non-parametric statistics, empirical explorations of the data, pattern finding, this sort of thing. Okay, so here's my perspective. Let's say there are maybe 4 or 5 aspects to climate change risk assessment. The first 4 are things that I think machine learning can help with quite a bit. Confidence in historical hydrometeorological baselines, really important to do a climate change risk assessment. Connection to large-scale ocean atmospheric climate drivers, really important. We want to predict things at the local scale, but there's so much noise that we need to connect to the larger regional and global drivers of local conditions. Machine learning is really helpful with that. Estimation of the performance of nature-based solutions, of our adaptations, of reservoirs too, but nature-based solutions in particular. Land modifications, soil moisture, the sorts of things that Professor Sheffield was just talking about. And water quality considerations, the area in which we just never have enough information at all. Those are all ripe places for machine learning to assist us. Okay, but we love talking about climate change adaptation as a bottom-up process. We mean bottom-up in terms of data because we want it to be super locally relevant in terms of the hydrometeorological data, but also bottom-up in terms of governance, in terms of administration, in terms of ownership of these adaptation strategies. We don't want to impose our external, Western maybe solutions to local people's problems. We want them to be creating their own solutions and owning them fully. So there's a risk when you do machine learning and you say, I'm going to survey the whole world and I'm going to superimpose upon you the solutions I discover when I train my model on Asia generally. Okay. So just a quick survey here, 30 seconds per slide, to show you how I think AI can help and where I think we can have some trouble, some roadblocks. Okay, here's an example from the Ohio River, my hometown. Cincinnati is somewhere in there. That's the United States. And there are dams, like lots and lots of dams. There's something like 10,000 dams that the U.S. Army Corps of Engineers manages east of the Rocky Mountains. Lots of dams, thousands of dams in the Ohio River Basin. It means that we have a really hard time figuring out what natural flow conditions are. So AI can help us to distinguish between modifications made to flow by the dams and what the natural conditions actually would be without the dams. Okay, South Africa. This is of particular concern here is Cape Town droughts. We want to understand what has been happening with Cape Town droughts in the last 30 years and make some sort of plan for what to invest to protect ourselves from future Cape Town droughts. The problem is that the local precipitation signal is super noisy, as precipitation signals always are. So we need to ground ourselves in a more distinguishable trend, which we can get if we take a step back from the local precipitation and look at regional climate drivers like weather regimes. These are pressure clusters around South Africa that dictate how much it rains in South Africa. Wonderful task for machine learning clustering analysis. Okay, we want to invest in nature-based solutions, which of course would cost us some money. So we want to know what we're talking about before we start doing all sorts of land use modifications and buying urban land and converting it. We don't have enough data on how much change a nature-based solution has made in the past to local flood and drought risk. So we can use clustering analysis again and machine learning techniques to survey global databases, global data sets of land use modifications from satellites or from whatever, and to inform ourselves in expectations for how much a certain land use modification might improve our infiltration, evaporation, and runoff. Okay, last one on what machine learning can help us with. Water quality. Water quality, we do floods and droughts first. We do water quantity modeling because water quality modeling is the step after water quantity modeling. And it's a cascading uncertainty of not having enough information. So we don't have enough information about water quality. But if we use machine learning and appeal to all of the indicators we can appeal to, that not just the water quantity, river stream flow, but also farmer behavior, pesticide application, all these sorts of things we can use to inform our expectations for water quality performance. This is, again, the Ohio River. Okay, and last slide here. This is the pitfalls, my concerns about applying machine learning to a bottom-up, a sort of a paradigm, a bottom-up paradigm, a philosophy of wanting local solutions to local problems. There's a risk when we survey the whole world and put that on a local problem that we could wash away the local perspective. So the road hazard here in this is the CRIDA process, right? The UNESCO CRIDA process. The road hazard is that we don't particularly want the local solution to be based on some kind of global survey necessarily. We don't want this to be a sort of big data thing. We want it not necessarily to be, we want the solution in Cape Town to not necessarily be based on trends throughout the continent of Africa. We want it to be based on what specifically is happening in Cape Town. That's my point about taking information from a large area and claiming that it is a solution to a local problem. Okay, I think that's it. Thank you so much. Close enough to 8 minutes, I think. Thank you for your attention. And I'm really excited about what's happening here. I'm really excited to talk to you. So let's continue to talk over lunch and later.